Hi students, welcome in chemistry classes. We are seeing the videos of thermodynamics. In our previous lecture, we have started the new playlist of thermodynamics. And in that lecture, you have seen various type of terms that are usually related with the thermodynamics and that you should know. Okay. Now there are some mathematics terms also that are related to thermodynamics. Some of the rules, some of the terms that are actually very important and that is related to thermodynamics, and if you don't know about them then you cannot do the questions of the thermodynamics. Okay, so I am giving you a basic of these terms. Okay, so see here, first of the term is partial derivatives and total differentiation. What is meaning of it? You have studied about the total differentiation and now you will see a new term, partial derivative. Sometimes you have written like this, dz upon dx. Okay, and sometimes you see that there is written in this manner, del z upon del x, like this. Okay, so what is the difference between this d and this del? This is d, this is d, and this is del. Actually this term is called the partial derivative. Okay, this is partial derivative and this is called the complete differentiation. Complete differentiation means, suppose if z is a function of x, then we can do its differentiation with respect to x. It means dz upon dx in this manner. Okay, about this whole thing I have told you in my lectures of the quantum mechanics. If you have seen my videos of quantum mechanics, I have made a complete playlist of quantum mechanics. Okay, first unit of the physical chemistry. So if you have not seen that, you can see that. Okay, here we have given the mathematics behind the quantum mechanics and I have told you about the total differentiation and integration rules. There are different type of formulas I have told you. Okay, so this is basically related there and I have told you about this. Okay, so this is called total differentiation. But now in thermodynamics you see a new term, this partial derivative. What is it? See here, suppose we are saying that z is a function of x and y. Okay, these are two variables, one is x and another one is y, and z is function of them. Okay, so we can do its differentiation with respect to both of them. Suppose one time we are doing the differentiation of z with respect to x, keeping y as the constant. Okay, we are doing differentiation of z with respect to x, keeping y constant. Then how we can write it? We will write in this manner. This term, this symbol is called del. Del z upon del x, and outside the bracket we will write here y. It means y is kept constant. So this is called the partial differentiation and this term will be called partial derivative. Okay, similarly we can do the differentiation of z with respect to y, keeping x constant. That can be written as del z upon del y at constant x. These both the terms are called the partial derivatives. Okay, and if z is a complete differentiation, exact differentiation, then how we can write its complete differentiation? So we can write it in this manner. dz is equal to del z upon del x at constant y dx plus del z upon del y at constant at x dy. This is called the complete differentiation. This is called the complete differentiation of z. Okay, so if z is a function of two terms x and y, then complete differentiation is done in this manner and partial derivatives are taken in this manner. Now there is one more term that is called Euler's Reciprocity Theorem. Okay, what is it? See here, as I have told you, suppose z is a function of x and y. Okay, if z is a state function, if z is a state function. What is meaning of state function? I have told you in my previous lecture. State function means if the value of z depends upon only the state. If the system is going from state A to state B, then the value of z depends only upon the state A and only upon the state B, but it does not depend upon the path. Then z is called a state function. So suppose z is a state function and it is a function of x and y, then it will be a exact differential. Okay, if z is a state function, then we can say it will be exact differential. It means we can do its complete differentiation. dz is equal to del z upon del x at constant y dx plus del z upon del y at constant x dy. This is called the exact differential. Okay, now suppose this term del z upon del x at constant y is called mxy. Okay, and this term del z upon del y at constant x is called nxy. Okay, we can write in this manner in a short way. So we can write that dz will be equal to mxy dx plus nxy dy. Okay. Now, if we want to take the second differentiation, it means if we are doing again the differentiation of this and this term, then how we can write del m upon del y at constant x. Okay, this will be equal to del square z del y del x. What is meaning of it? See here, this mxy means the differentiation of z with respect to x at constant y. Now we are doing again its differentiation. So again its differentiation will be with respect to del y. Okay, because we have firstly done the differentiation with respect to x. So this term del m upon del y at constant x will be equal to del square z upon del y del x. Similarly, the term del n upon del x at constant y will be equal to del square z upon del x del y. Okay. Now, the Euler's reciprocity theorem says that this del square z upon del y del x will be equal to del square z upon del x del y. Or we can say del m upon del y x will be equal to del n upon del x at constant y. This is called the Euler's reciprocity theorem. Okay, this is called the Euler's reciprocity theorem. Why? Because this theorem says that if z is an exact differentiation or if z is a state function, then it does not matter what is the order of the differentiation. We can do any differentiation first and we can do any differentiation second. It means suppose we are doing the differentiation of z with respect to x firstly and then we are doing the differentiation of z with respect to y. And if we are doing the differentiation of z with respect to y firstly and then we are doing the differentiation of z with respect to x, it does not matter. In both the cases the result will be same. It means the second differential of the state function will be same whatever will be the order. This says the Euler's reciprocity theorem. I hope this thing is clear to you. We can understand it with the help of an example. See here one of the example. Suppose we are seeing the pressure term. Okay. Pressure is a state function. Okay. Pressure is a state function and we can prove it with the help of Euler's reciprocity theorem. We know about the ideal gas equation. PV is equal to RT for 1 mole. Okay. So we can write P is equal to RT upon V. Right? Okay. Now we can do its differentiation. The differentiation of P, we can do the differentiation of P with two terms. Okay, we know that P is a function of T and V. Okay, these two are the variables and P is changing with respect to them. So we can do its differentiation with respect to them. Firstly, what we are doing? We are doing the differentiation of P with respect to T. Del P upon del T at constant V. We have put the volume constant. So what we are getting? This is our equation. Okay, this one. See here. So we are doing the differentiation. So we are getting del upon del T RT upon V. This thing is done at the constant volume. So what will happen? This R and V will be constant. Okay, because volume we have taken constant. So R upon V comes outside. And the differentiation of del T upon del T will be equal to 1. So we are getting R upon V into 1 means R upon V. Okay. Now we do the differentiation of del P upon del T with respect to V. Okay, we are doing the second differentiation of the pressure. We are taking its second derivative. So what we are getting? Del upon del V R upon V. We can write it. Okay, now this is the volume and this is volume. The differentiation of 1 upon V will be equal to minus 1 upon V square. Okay, so we are getting minus R upon V square. This will be the result of this thing. Okay, del square P upon del V del T. We can write it in this manner. This is second differentiation. Okay, now see the next thing. We can again do the same thing in a different order. We know P is the function of T and V. So we can do the differentiation of pressure with respect to volume first, keeping the temperature constant. Okay. So our term is P is equal to RT upon V. So write here del upon del V RT upon V. Here RT will be constant. So it comes outside. Okay. And the volume 1 upon V, its differentiation will be equal to minus 1 upon V square. Okay. So we are getting minus RT upon V square. Now do second differentiation. It means del P upon del V and then write here del upon del T. Okay. So what we are getting? This. See here minus RT upon V square. Now we are doing the differentiation with respect to temperature. So volume will be constant and R is again a constant. So these terms go outside. Okay. And differentiation of T with respect to T will be equal to 1. So what we are getting? Minus R upon V square. This was the second derivative in this manner. Okay. So you can see that here the order is different. Here the order is different. But we are getting the same result. Minus R upon V square minus R upon V square. So we can say del square P upon del V del T is equal to del square P del T del V. It means whether which is the order, it does not matter. The thing is that it is the state function, so it is following the Euler's Reciprocity Theorem. It means its second derivative will remain same whatever is the order. Okay. Now there is one more important term that is called exact differential and state function. What is the relationship between the exact differential and the state function? Actually see here, if d phi xy means phi is a function of x and y. If it is a exact differential, suppose it is a exact differential. So if it is a exact differential, then the integral of d phi xy between 2 points will be the function of endpoints only. Okay, we can write the integral of d phi xy between any 2 points will be function of endpoints only and will be independent of path. Means to say whether which state function we are taking, in all the cases their integral between two limits will be the function of only endpoints. It does not depend upon the path. We can write in this manner d phi xy, if we are taking its integral between two limits a and b, then we can write it in this manner phi xy b a. Okay, and we can write it phi b minus phi a. or we can write it delta phi. Okay, so integration of d phi between the limits b and a will be equal to their difference, means phi b minus phi a, or we can write it del phi. Similarly, if we are doing the differentiation of internal energy, suppose we are taking integral of internal energy, then this will be equal to ub minus ua. It means internal energy of the state b minus internal energy of state a, or it will be equal to delta u. It means it does not depends upon the path. Okay. Further, if we are taking the cyclic integral is shown in this manner. Okay, d phi xy, this will be equal to b to a d phi xy plus a b d phi xy, and this will be equal to 0. Or we can say that limits b to a d phi xy will be equal to minus limits a to b d phi xy. Okay, so any state function you are taking always fulfill this requirement. This is a cyclic integral. Okay, so this both the things, the limit b to a d phi will be equal to minus limits a to b d phi. Now see the essential criteria for a state function. How any term can be a state function. Okay, so for this some criteria are there. First of all, first point is that change in value of a state function depends only on initial and final state and not on the path of process. Means to say, du, we are taking du, then in the limits b to a, this thing depends only upon the state b and state a. So its value will be always ub minus ua will be equal to del u. It does not depends upon the path. Okay. Similarly, the cyclic integration involving a state function is always 0. It means if we are taking the integration b to a du, that is a function of xy, anything, this is maybe a function of temperature and pressure, we can write here temperature and pressure, suppose. Okay, so this will be equal to minus a to b du tp. Okay, third point says that the state function has an exact differential. It means, suppose if we are taking p is a function of t and v. Okay, suppose we are taking pressure, it is a state function, and it is a function of temperature and volume, then it will be exact differential. So we can write dp is equal to del p upon del t at constant v dt plus del p upon del v at constant t dv. Okay. Similarly, you can write to du. Du is a function of temperature and volume. Suppose it is a function of temperature and volume. Then we can write del u upon del t at constant volume dt plus del u upon del v at constant t dv. Okay, because these are the exact differential. Okay, and secondly, this will follow the Euler's reciprocity theorem. It means this dp, suppose we are taking this, as I have told you, we can write the differentiation del p upon del t at constant v, and again we are doing its differentiation with respect to v at constant temperature. This will be equal to del upon del t, del p upon del v at constant t, and this whole and constant v. It means this should follow the Euler's reciprocity theorem. Suppose we are seeing the volume. Second example may be volume. Volume of a fixed amount of ideal gas. Volume of fixed amount of ideal gas is a state function. It means its value depends only upon the states, does not depend upon the path. We can use the ideal gas equation for it. PV is equal to nRT, or we can write V is equal to nRT upon P, right? So similarly, we can do the same thing as we have done in the case of the pressure. Del V upon del T at constant P will be equal to, see here, del V upon del T at constant P will be equal to del upon del T of nRT upon P, right? Now this term nR upon P is a constant, so it goes outside, okay? And the differentiation of temperature with respect to temperature will be equal to 1. So this term comes nR upon P. Now again you can do its differentiation, del V upon del T, and again we can do its differentiation, means we can do del upon del P. So this term now comes del upon del P nR upon P. Now the differentiation of P, 1 upon P with respect to P will be equal to minus 1 upon P square. Okay, and this term nR will go outside. So we are getting minus nR upon P square. Okay, similarly we can do in the second method, second order. We can take firstly the differentiation with respect to pressure, keeping the temperature constant. So what we are getting? Del upon del P, nRT upon P. Okay, so this nRT term will go outside, and the differentiation of 1 upon P with respect to P will be equal to minus 1 upon P square. So we are getting minus nRT upon P square. Okay, now do its second differentiation. So del upon del T, del V upon del P. Okay, this will be equal to, now see here, del upon del T of, we have taken the minus term outside. Okay, so this will go in this manner. Okay, nR upon P square will be a constant, so put it outside, and the differentiation of temperature with respect to temperature will be equal to 1. So this term comes minus nR upon P square. So you can see both the side we are getting the same value. It means this is following the Euler's Reciprocity Theorem. So we can say volume is a state function. Okay. Actually in thermodynamics we use several state functions. State functions means the functions which are only a function of the state. It does not depend upon the path, and secondly it follows the Euler's Reciprocity Theorem, and thirdly it is exact differential. So some of the state functions that are used in the thermodynamics are, first is internal energy. This is internal energy. We see always the change in internal energy, and its formula is Q plus W. I am giving just a short view of this. The whole things we will see in detail in our next lectures. Okay, these whole topics will have, each and every topic will have a single lecture. Okay, so don't worry, just I am telling you about the state function in a little while. Okay, so first state function may be internal energy, second is enthalpy. This is also a state function, and its formula is H is equal to U plus PV. Third is S, entropy, and for this the formula is Q reversible divided by absolute temperature. Okay, next state function is G, Gibbs free energy, and this is given by G is equal to H minus Ts. And okay, next is A, this is called Helmholtz free energy, and this is given by U minus Ts. This is also called work function. Okay, I will give you the complete topics in detail, so don't worry, just I am giving you a little bit so that you can do each and everything very quickly. And one more thing is the mu I, that is called chemical potential, and this is given by del G upon del Ni at constant temperature, pressure and number of moles of other components. Okay, so these are some of the state functions. Now there are some rules that are related to thermodynamics and that are applicable in thermodynamics. Okay, so I am giving you a little bit about them here, because when we will start the Maxwell relationships and the other topics like the thermodynamic coefficients, these rules will be used. Okay, so I am giving you a little bit. Whenever we see the partial derivatives, this reciprocal rule is used in the case of the partial derivatives when we see their Maxwell relationships. Okay, in our next lecture we will start the Maxwell relationship, but see here, whenever we use the partial derivatives, we use the reciprocal rule. And reciprocal rule says that if del x upon del y at constant z is equal to del a upon del b at constant c, then we can write del y upon del x at constant z will be equal to del b upon del a at constant c. It means this and this one will be reciprocal. Okay, this one and this one terms, this term and this term will be reciprocal of each other, or in other words we can write del x upon del y at constant z is equal to 1 upon del y upon del x at constant z. This is called the reciprocal rule. Okay, this is the reciprocal rule. One more important rule is the cyclic rule. So see here what the cyclic rule says. Cyclic rule says if P, V and T are three variables. Okay, if pressure, volume and temperature are three variables, then write in this way: pressure, temperature, volume. Okay, you can write in this manner. Write here temperature, here pressure and here volume. Then we can write that del P upon this, del P upon del V at constant temperature, del P upon del V at constant temperature into, then write del V upon del T at constant pressure, del V upon del T at constant pressure multiplied with del T upon del P at constant volume. Okay, this whole thing will be equal to -1. Okay, just you have to go in the cycle. Del P upon del V at constant temperature will be equal to del V upon del T at constant pressure, and this will be equal to del T upon del P at constant volume. Okay, and this whole, the multiplication of them will be equal to -1. So this is the cyclic rule. How this rule is used, why we are writing here this rule, this is very important, and this we will see whenever you will see the thermodynamic coefficients, thermodynamic expansion coefficient, alpha, beta, gamma. We will study about them, we will derive about them. So there you will use the cyclic rule, and the reciprocal rule you will use in the Maxwell relationships. Okay, so both the rules are quite important, and the importance of Euler's theorem you have seen just now. Okay, so this is all about the mathematics behind the thermodynamics. Okay, this video is quite efficient for you if you are from a biological background. Okay, if you don't know about some math, and if you are from the biological background, then you should cover this video fully. Okay, and if you are liking these videos, please share it with other students. Please subscribe the channel, and if you are liking videos, please comment me. Okay, thank you.